Let me begin with a word of prayer. So, Dearly Father, we thank you for this day. I thank you for these students. I just ask you bless our work today. Help us to glorify you, what we do. And I just pray that all the students would ask good questions as they have them, Lord. In your name I pray, Lord Jesus. Amen. Okay, so last class I told you about number systems, and we talked a little bit at the end about what a prime number is, right? A prime number is a number which is one which only has itself and 1 as divisors, right? So like 2 is prime, 3 is prime, 5 is prime, right? And so one of the fundamental problems really since the time of the ancients has been to find these prime numbers, right? And so the handout that I gave you guys is a method that was, I think, invented by this ancient Greek mathematicians, Eratosthenes. Interesting guy. He was a contemporary of Archimedes. He lived around like 250 BC, something like that. I was reading his sort of life story on Wikipedia yesterday. It's interesting. He lived to 82. He lost his eyesight, and according to what it says there, he just starved himself to death. It's kind of a dark end, but you know, this is, you never know what you're going to find. But let me just show you this. This is called the sieve of Eratosthenes here, and just for fun, let's work it out together. This is a method to find all the prime numbers, and so let me just kind of show you how it works. All right. So, like the full thing to do is to write out all of the numbers up to whatever number you're interested in, and then you cross out multiples of primes. So like 2 is the only even prime, right? Like if you have any even number which is larger than 2, it's not prime, right? For example, 14 is not prime because 14 is 2 times 7, right? So it has divisors of 2 and 7, which means it's composite, which means it's not prime. So like the only even prime is 2. So setting aside that, right, you can put that at the start. There's a 2 before all this. Okay, great. I already got rid of all the multiples of 2 to make it more interesting. We can start with 3. What are any multiple of 3 is not prime, right? Like 3 times, well, 3 times 2 is 6. I already got rid of that. But what's 3 times 3? 9. So I cross out 9. What else is a multiple of 3? 15, 21, 27. 3 times 11 is 33. 3 times 13, 39. What's the next one? 3 times 14 is, 42, that's out. 3 times 15, 45. 3 times 17 is 51. 3 times 19 is 57. 3 times 21, 63. 3 times 23 is 69. 3 times 25 is 75. Let's see here. 81 is a multiple of 3, right? What else is a multiple of 3 here? 3 times 87 is a multiple of 3. 93 is a multiple of 3. 99, multiple of 3. Let's see here. I'm trying to think.
105?
Is 105 a multiple of 3? 105 is... 102 is multiple of 3? Okay.
11.
Is 105 is multiple of 3? Yeah. Thank you, because you add 6 to 99. Very good. If I add 3 to that, I get 108. Then 111 is a multiple of 3. Add another 3, we get 114, another 3, we get 117 is a multiple of 3. 123 is a multiple of 3. So we're just looking for, like, add 3. 126 plus another 3 is 129. That's a multiple of 3. Add another 3, I get 132 plus another 3 is 135. Add another 3, I get 138. Add another 3, I get 141. Add 3, I get 144. Add another 3, I get 147. Add another 3, I get 150. Add another 3, I get 153. Add another 3, 156, 159. 162 plus 3 is 165. Plus 3 is 1. Okay, there. Though, okay. Oh, that's the hardest one. Those are all the multiples of 3. All right, we've crossed out all multiples of 3. See, none of those could be prime, right? Because they're all multiples of 3, which means they're composite. Yeah? And then we can cross out multiples of 5. This will be easier. I'll do it in blue. So there's 5. What's the next multiple of 5? 10, 15, 20, 25. There's one. 30, 35, 40, 45, 50, 55, 60, 65, 70, 75, 80, 85, 90, 95, 100, 105, 110, 115, 125, 145, 155. All right, so there you go. That's all the multiples of 5, right? You notice that some of those multiples were already gotten rid of because they also were multiples of 3, right? Okay, so what's up next? 7. We look for multiples of 7. I'm going to cross those out in green. All right?
Bless you.
So 7, then we go what? 7, 14, 21, 28, 35. What's the next multiple of 7? 42, 49. Oh, there's 49. 56, 63, 70, 77. There it is, the multiple of 7. Add another 7 to that, I get 84, 91. 91 plus 7 is 98, plus 7 is 105, plus 7 is 112, plus 7 is 119, plus 7, 126, plus 7, 133, add 7, 140, 147, 154, 161. Hopefully I didn't make an arithmetic mistake here. Add 7 to 161, I get 168. Okay, great. All right, what's next? 11. So you got 11, 22, 33, 44, 55, 66, 77, 88, 99. What comes after 99 in terms of multiple 11? 110, right? That's gone already. 121 is 11 squared. And what's 11 times 12? Oh, that's not going to be in here. That's even. 11 times 13 is what? I'm going to cheat. What's 11 times 13? I get 153. You said 143. Did I do that wrong? I might have. 143. I've somehow made it 153. What's wrong with me? So 143 it is. Is that already gone? Nope. Oh, there it is. And then let's see here. 11 times. What was that? 11 times 13.
It would be 154.
11 times.
5.
What's next? 154, and then add 11, 165, it's already gone. Okay, so there we go. We got multiples of 11. What's next? 13. Let me do that one in purple. So we got 13, 26, 39. Add 4 times 13 is what? 52, add 13, 65, add 13, 78, add 13, 91, add 13, 104, add 13, 104 plus 13 is 117, add another 13, 130, add another 143, add another 13, 156, add another 13, 169, right? 13 squared is 169. Okay, so there's a theorem, guys, and the theorem is this, that prime, well, basically you only need to check up to the square root of the number here because of the way the primes work. So what do we have left? Let's circle everything that's left. What do we got? I mean, 2 before, 3, 5, 7, 11, 13, 17, 19, 23, 29, 31, 37, 41, 43, 47, 53, 59, 61, 67, 71, 73, 79, 83, 89, 97, 101, 103, 107, 109, 113, 127, that feels wrong. No, it is. All right, what is it? 131, 137, 139, 149, 151, 157, 163, 167. If I haven't made a stupid arithmetic mistake, those are all the primes up to 169. And so this is known as the sieve of Eratosthenes. I think it's kind of a neat, I mean, it's a fun thing to do, yeah? Well, maybe my idea of fun is different, but do you want to check our answer? We could check, right? I'm kind of nervous to check my answer. Let's see here. All right, guys, you got them, right? So let's look at the other. How do we do? Come on. 2, 3, 5, 7, 11, 13, 17, 19, 23, 29, 31, 37, 41, 43, 47, 53, 59, 61, 67, 71, 73, 79, 89, 83, 89, 97, 101, 103, 107, 109, 113, 127, 131, 137, 139, 149, 151, 157, 163, and 167. There are 39 primes. Is that what we got? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36, 37, 38, 39. It said 39, right? Okay, phew. All right. So my original interest in counting wasn't really mathematical. It had more to do with the game of hide and go seek. You know, because there's this rule that you had to count to a certain number before you could go seek the other people. So like the faster you could count. As a slow person, this is important, right? So if I can count faster. Do you guys play that game? No? Do you slow the counting down with like Mississippi's or something? Like 100 Mississippi's would be like 1 MISSI, SSI, PPI, 2 MISSI, SCP, you know, like that. No? Yes? No? Had another word you used? No? Oh. You just counted? No, okay. I'm from a simpler time. We had more time. Let's see here. Okay, so. I don't have, I have a little bit more to say about primes. Let me just talk just a bit more here about it. Do you guys notice any particular patterns in these numbers? There's things called twin primes. Do you know what a twin prime is? They're primes that come like sequential odd, like successive odd numbers that are both prime. There's a few of them in here, right? Like, well, 3 and 5 and 5 and 7. These are both twin primes. 11 and 13. Successive odd numbers, they're both prime. 17 and 19. There's another pair of twin primes, right? 29 and 31. That's another pair of prime success. See it? There's a bunch of them in here. See it? 29, 31, 59, 61, 71, 73. 101, 103 is another. 107, 109. 137, 139. See that? So there's something called the something called the twin prime conjecture, which conjectures that this keeps happening forever and ever. But it's one of those like standing unsolved problems in number theory for quite some time now. There's a lot of problems like this in number theory which are relatively easy to state, but they're really hard to solve. So one of the things your book talks about, and we can talk a little bit about, is this problem, right? X to the n plus y to the n equals z to the n for integers x, y, and z. So this equation has been studied for like a long time. And when n equals to 2, there's all kinds of solutions known for this. In fact, that has somewhat to do with what we're talking about today with the Euclidean geometry. See this? If you have like x squared plus y squared equals to z squared, a set like this is called a Pythagorean triple. So for example, if you have a triangle, right? You guys have ever heard of the 3, 4, 5 triangle? So if it's a right triangle, you notice that 3 squared plus 4 squared equals to 5 squared. Do you guys agree? So 9 plus 16 is 25. Did you know that if you know that that triangle works, you can take that triangle and rescale it? Like if we just multiply each side in the triangle by 2, it gives me an 8, 6, 10 triangle. And did you know that 6 squared plus 8 squared is equal to 10 squared? You can do that. That's still true, right? Because 36 plus 64 is 100. And that's kind of neat, right? But you could also multiply the triangle by 13, and that would still be another solution to this n equals 2 problem. 13 times 5 is 65. 13 times 3 is 39. 13 times 4 is 42. And I bet nobody in here knew that 42 squared plus 39 squared is equal to 65 squared, right? I don't think I knew it before I wrote this triangle down. And once you get this trick in your system, you see, oh my goodness, well, if I just know one Pythagorean triple, I can generate thousands and thousands of other solutions, right? This kind of thinking, we're pretty sure was known by like the ancient Babylonians. This particular corner of mathematics is well explored because it's connected to how you situate triangles with their sides and their hypotenuse, right? So there's an obvious geometric application to this. This is old mathematics. So it's not surprising that people were looking at this equation here. See? This equation is sort of just the more general version of that. Instead of just putting n equals to 2, allow n to be larger, right? So here's the weird thing. If n is greater than or equal to 3, there are no interesting solutions. What do I mean by interesting? Interesting, I mean they're all non-zero, right? Of course you could put x equals to 0 and you could put y equals to z, it solves it, right? We're not interested in that. So interesting solutions would be, y and z both non-zero and z also non-zero. And this little thing I circled in green, this is known as Fermat's last theorem, which is an interesting bit of math because it remained unsolved from the time of Fermat till, I don't know, let's see here now, about 30 years ago, maybe 20 years ago, I forget exactly, I think 30. I believe it was 92 this got solved, somewhere in there. there's a fellow named, professor named Andrew Wiles. I think about 92. I'm a little fuzzy on that. It's in your book, the precise date, but so Fermat just scribbled in a margin to a book by one of the great ancient Greek mathematicians, I believe. I think it was Diophantus. He scribbled in the margin of one of the library books around 1650, something like that, I think, that, you know, this had no solution, and he had a simple proof for it, but it wouldn't fit in the margin. And so people tried to prove it for hundreds of years, and no one could find a simple proof, and it's just like, did Fermat really know a proof? Or is he just full of nonsense? I mean, so whether or not Fermat actually knew a proof of that theorem or not, we don't really much care. Because what's interesting is that the proof that was found by Andrew Wiles has really opened up and revolutionized the study of number theory in the last, 30 years or so. So the techniques and tools that were used by this guy to solve that problem have excited and motivated generations of new mathematicians to explore this kind of mathematics. And the interesting thing is about all this is beyond just, you know, solving hundreds of year old theorems. When you pursue number theory more fully, you get an understanding of primes, and this feeds into the problem of encryption. So let me talk a little bit about the idea of encryption. Well, I don't really have formulas to share with you. Let me just be vague and talk about it. So basically, the idea of encryption is that you share a number publicly, right, with everybody. And the thing is, that number is formed by the product of a couple of prime numbers. But the prime numbers are so huge, they have like hundreds of digits, right? And so if you know how that huge number is formed by a product of the two prime numbers, it allows you like to unlock certain mathematical properties of it. And so you can sort of undo that number. But the only way you can undo the number is to know the numbers which are making up this big number. And so that is used to, that basically is used to form the basis for encryption. In other words, the whole idea of encryption rests on the impossibility of factoring really big numbers into a product of primes. You know, if I give you a 100-digit number, how do you decide whether or not that number is prime? You think about this? You probably can't do what we did today, right? You're not going to take a giant sheet of paper and write out all the numbers up to, you know, a 100-digit number. That would take a lot of paper and too much time. It was kind of troublesome for us to even do the up to 169, wasn't it? So this is a pretty much well-known difficult problem in mathematics, is finding all the prime factors of a large number. It's just a computationally difficult problem, and because of that, you can hide things in plain sight because of this difficulty. This is how all of our encryption is basically resting on. If you could find an efficient way to factor really, really large numbers into a product of primes, you could hack into everybody's email, everybody's bank account, everything, right? So it's kind of a big deal. And I don't know, to me this is all very funny because, you know, 100 years ago, there were a number of theorists who took a lot of pride in the fact that this kind of mathematics was pretty much unapplicable. Like looking at prime factorization of numbers, it had no direct application to the real world, unlike, say, calculus or other things in mathematics, which have always been applied to science and engineering. And I think the great irony is that now this kind of unapplicable mathematics is actually applied to pretty much everything that we do in commerce. And like pretty much all of your electronic communications is encrypted, right? Well, hopefully. I mean, I guess communicate at your own risk. You're like, I got nothing to hide. I don't need encryption, right? That's what my brother said back in the Bush years. Oh well. Anyway, so that's all I've got to say about primes, I think. The other thing I could talk, do you have a homework problem on divisibility? So I suppose I could talk for a minute about that. There's something interesting there to talk about. So, rule of nines. Do you guys know about the rule of nines? So, here's the thing. If we have a number, n, right, and it's got the base 10 expansion of, let's say, you know, ak times 10 to the k plus ak minus 1 times 10 to the k minus 1 plus dot 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 plus a2 times 10 squared plus a1 times 10 plus a0. So this would be our typical number, right? ak minus 1 dot 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 a1 a0, and we don't usually write this, but if we were, we could write 10, right? So this is the base 10 expansion. Now, there's an interesting kind of mathematics that you can do, which is called modular arithmetic. So arithmetic modulo 9 works like this. So let's put a bar over things. So here's the way it works. Like, let me just give you some examples. If I have 3 plus 7, and this is done mod 9, that gives us 10, all right? But 10 is 1 plus 9. And the deal is, copies of 9 go away. Basically, in mod 9 arithmetic, any multiple of 9 is 0. So, like, for example, if I have 3 times 6, I would get, 18. But since 18 is 2 times 9, and 9 is 0 mod 9, we get 0. So this is the way mod 9 arithmetic works, is it just absorbs copies of 9, right? Do you guys know any arithmetic that's kind of like this? You have some experience with it, actually, in your daily life. This is the way time works, right? Like, if you think about the minutes in an hour, it's always working sort of like mod 60, right? If we add, what time is it right now? 10:24, right? So if we're 80 minutes past now, how many minutes are we after the hour? 24 plus 80 is what? 104? So if you get rid of 60 of that, it's left you with 44. We're at 44 minutes after the hour. That's mod 60 arithmetic, if you just get rid of 60 copies of 60 and set them to 0. So like clock arithmetic involves modular arithmetic. Just another example here. If I have, let's see here. So what I said 10 is equal to 1. What's 10 bars squared equal to? 10 times 10. Mod 9 is what? That's 1 times 1, right? Which is 1. In fact, 10 to any power, check this out, 10 to any power is equal to 1, mod 9. All right? So what that means is if we look at my token number up at the top, right? If we look at the token number I have up at the top, and if I look at n bar, maybe I should make that an m. N bar, then I've got, ak times 10 to the k, plus, I'll just get rid of the other one, plus dot 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 plus a2 10 squared, plus a1 times 10, plus a0, right? And if I calculate that number, mod 9, what happens? I get ak times 10 to the k. So the modular arithmetic works like this, you can break it up across multiples and sums, like so. And what did we just say about 10 to any power? Well, 10 to any power mod 9 is 1. So this is 1, that's 1, these are all 1. What you're left with is a sum of the coefficient, sum of the digits in the number, mod 9. Which we could rewrite like this. You just add the digits, and you can simplify the sum of the digits modulo 9. Now here's the theorem, rule of nines. The theorem is just this. N is multiple of 9 if the sum of its digits are divisible by 9. And this algebra I'm showing you on this page proves that. All right? Like, because to say that a number mod n, mod 9 is 0 is to say it's divisible by 9, actually. And let's try this out. So if we take, like, 1400, 607, is that divisible by 9? Well, let's see here. 1 plus 4 plus 6 plus 7 is equal to what? 5. What do we got? 10 plus is 18, isn't it? Is that right?
Yeah.
That is 2 times 9. So, yes. 1467 divisible by 9. Now, some of you are getting calculators out because you don't believe me, and I respect that. Trust but verify. The last great American president said this, yes? Is that a not a quote from Trump, but anyway. Let's see here. I like Trump, what am I saying? But here's 4, 6, 6, 7. What do you guys think? Is Trump going to run? Let's see here, 1467. Seems kind of old to run. I mean, physically, I was trying to make a joke about physical running, but it didn't work. Let's see here. So 163 times 9 is actually that. So there you go. In contrast, if you just, so this is the rule of 9s. And so anyway, any questions? Your text has like this big table of divisibility tests. I don't want to derive all of them, but I think this one's interesting to derive. If you want to talk to me more about this in office hours, I'm happy to talk to you more about it. This is called modular arithmetic. I don't think I've included, there's a section in your book which actually has problems on this to do, but I don't think I put that in your course, so this is kind of as far as it's going to go for us here. Mostly I just want you to be aware of that. So. Any questions about homework then? Let me go forward here. What was that page? I guess the sieve of the Eratosthenes was page 2. And this would be page 3. Let me shift over to geometry, and I think what we'll do is, so we're now in chapter, what chapter are we in here? Chapter 7. And I don't think I cover all of chapter 7, but chapter 7, which is on measurement and geometry. Sorry, I can't spell. 3, 4. So let's just start carving away some examples here from the homework, things like the homework at least. I think you're going to find the homework from this chapter rather relaxing if you enjoyed geometry in like elementary school. If you did not enjoy geometry in elementary school or high school or whatever, this might be less fun, but let's see here. So example 1 actually wasn't even geometry. It was just very silly. So like, let's, how many meters in 1 mile? So to work a problem like this, we need to be given some like conversion ratios, right? Like, let me share some facts with us, some facts with you. How much is a mile in terms of feet? A mile is 5,280 feet, all right? All right, so this is just a regular, typical mile. A meter, how much is a meter in terms of feet? A meter is 3.281 feet, all right? So if I know those two things, I can convert a mile to meters, right? Let's do that. So I'll show you how to do it. And the way I do it, and you know, if you have a different way of doing it, which makes more sense to you, then great. But this is how I think about it. 1 mile. And then I take 1 mile and I multiply by 5,280 feet over 1 mile. Right? So that, what am I doing? I'm multiplying by 1, right? That's a conversion factor. What I'm doing is I'm trading miles for feet. You see that? The miles cancel, and we're left with feet. And then what do? I multiply by another conversion factor, right? I multiply by meter, which a lot of times people just use an M for. Meter divided by 3.281 feet, right? So the feet cancel, and the miles cancel. Do you see that? We cancel them. I don't know what it was. Oh well. The miles cancels, the feet cancel, and I just need to get out my calculator, and we can figure it out, right? So let's see here, 5,280 divided by 3. Oh, come on, 3.281. What do we get? Whoa. Nice. That. See, if I asked you to do that, you couldn't do it, though. See here, 1609.3, let's say, meters. Do you guys recognize this at all? No? Well, that's okay. Another thing we can do is use a multiplier, right? A lot of times in science and engineering, people like to use multipliers. And so the multiplier that's popular to use here is K is equal to 10 to the third, which is 1,000, right? So if I want to rewrite this, I could rewrite this as 1.6093 km, right? So another way to look at this is 1 mile is 1.6093 kilometers, which, you know, you've heard of kilometers, right? Yeah. So example 2, we could like convert, suppose you got 100 kilometers per hour. How many miles per hour? How would you figure that out? So we've got like 100 kilometers per hour. And if I want to convert that to miles, what could I do? Use the previous example, right? The previous example, I just learned what? In the previous example, I just learned that 1 mile equals 1.6093 kilometers, right? So I can use that down here. I can say, well, a mile divided by 1.6093 kilometers, and see, I'm just multiplying by 1 there. And when I multiply that out, my kilometers, they're canceling, and we get 100. What's 100 divided by 1.609? So we get 62.15 miles over hour, right? Which we usually write as 62.15 miles per hour. So, you know, if you've got some sort of fancy new supercar and you want to talk about how awesome it is, do you want to use miles per hour or do you want to use kilometers per hour? You definitely want to use kilometers per hour because it sounds way cooler, right? Like 0 to 100 kilometers an hour in 3 seconds is you know, less impressive than 0 to 60 in 3 seconds. Although I wouldn't mind having a car that could do either. So, I don't know about you. Although I'm not sure I have enough money to pay the tickets around here. Any questions? All right, so that's the first thing in the homework. There's just some like conversion problems like that. I think the one in the homework is weight in terms of kilograms versus pounds. So let me work one just like the homework. So let's see here. The one in the homework is something like you got kilograms. So suppose Bob weighs, quote unquote weighs. That kind of bothers me as a physics instructor to even write this. But anyway, Bob weighs, let's say, 50 kilograms. How many pounds? The reason that bothers me is like kilogram is a unit of mass, and it's not a weight technically speaking. But anyway, what's the conversion ratio for how many kilograms and how do pounds and kilograms relate? Do you guys know? 1 kilogram equals 2.2 pounds. I think that's right. So then 50 kilograms we could write as this. This is 50 times what? 2.2 pounds. So I've given up on my multiplication by 1 idea for this one and just made a straight substitution, which is also fine. So we got 50 times 2.2. We get 110 pounds. All right, so there's that. Let's look at some more problems. Problem, page 5 here. So we're on example 4. So suppose you've got a line, and you've got point A, you've got point B, you've got point C, and you got point D. All right? Oops. You guys got to stop me when I'm writing off the edge of the world here. And you're told that you're given a few facts and figures here. You're given that AB is 10 centimeters. You're given that CD is 7 centimeters. You're given that AD is 37 centimeters. And you're supposed to find the length of BC. So how are we going to do that? Let's see here. So what I do when I'm faced with a problem like this is I just try to like draw on the picture and try to understand what the numbers mean directly in terms of the geometry here, in terms of the picture. So AB is 10, right? So it's 10 centimeters from here to here, right? CD is 7 centimeters, so it's 7 centimeters from here to here, right? The length of BC is what I don't know. Let me call that X, right? So here's what I'm trying to find out, X. And what else do I know? Oh, I know that the length from A to D is 37. So what does this tell me? Aha! So if you go all the way from here to there, you've got 37, right? So what equation does this give us? This gives us that 37 centimeters, right, is equal to 10 centimeters plus the thing we don't know, X, plus 7 centimeters. So we can solve for X, right? X is equal to what? 37 centimeters minus 10 centimeters minus 7 centimeters. I'm putting you guys to sleep. Let's see here. I accept it. Let's see here. 20 centimeters. I hope that's the answer. Whew. Okay, good. Yes. So this is like problem 2 in your homework here. Let's look at another one. Any questions? The basic idea here is that if we have points on a straight line, then the sum of the distances has to be the net distance, right? It's just that. 6 here. This one is about angles. So here you've got a picture that looks something like this. You got 3 rays coming out of an origin. All right. And I'll use some color coding here so you can see it better. We've got 74 degrees here, all right? And you've got 145 degrees out to there. And let's see here, while we're on the topic of angles and everything, can you guys tell me which one of these angles is acute and which one of these angles is obtuse? Right. So find x. Measure of angle x. All right. This is my example 5. So I heard that 74 degrees is acute. And the 145 is what? Is obtuse. What do those mean more technically? Acute means less than 90 degrees. Obtuse means bigger than 90 degrees, right? And I suppose less than 180. So what do you guys think here about x? What's the measure of x? We've got what? We've got x plus 74 equals to what? 145 degrees. Do you guys see that? So if we sweep from here to here and then from there to there, it's the same as sweeping all the way from all the way. So that gives me 145 is x plus 74, which gives me x is equal to 145 minus 74, which is what? 71 degrees. So that's like number 3 in the homework from week 12, yeah? All right, let me skip ahead to one that's a little bit trickier. And so I'll make it a little bit different than the homework, but something kind of like the homework. Example 6. All right, so let's suppose you've got angles like this, and just for the sake of discussion, let's suppose that this angle is x, and this one is actually 1.2x, and this one is 1.5x. This is 0.7x, and over here we've got 0.8x. All right? And this, and on the bottom is a straight line, okay? My question is, what is x? So I'm telling you that we have a straight line on the bottom, and so the idea here is if we have the sum of the angles over a straight line, the sum of the angles is 180 degrees, right? So we would have 180 degrees is x plus 1.2x plus 1.5x plus 0.7x plus 0.8x, and what would that give us? Um, 5.2x, right? So therefore x is equal to 180 degrees divided by 5.2, also known as 34.62 degrees, approximately speaking. I just rounded off to the hundredths place there, okay? So I don't know if there's a problem quite like this in your homework. There's one in your homework that's more like the following. So in the homework, it's got something more like this. All right. And so these, you got these 4 or 5 lines coming out of a central point, and you're told that like maybe this is angle x, this is angle twice x. Over here you've got, I don't know, again a 2x, and maybe over here you've got like a 3x. And then the question is, what's x again? What angle is x, right? How would you do this problem? It's a little bit different, right? See, here you're going all the way around, right? So if you go all the way around, that's 360 degrees. So we would put 360 degrees equal to, x plus 2x plus 2x plus 3x, yeah? Which would be, what, 3, 5, 8x? So x would be equal to 360 degrees divided by 8. Whatever that is for this problem. Ah, 45. So 45 degrees would be the answer there. So that is essentially how to do problem number 5 in your homework, okay? And actually, example 6 is relevant to number 4 in the homework. All right. Keep losing my phone here. Example 8. So I hope you don't mind that I'm just approaching Euclidean geometry by working problems, right? Like I could try to give you some sort of systematic exposition of Euclidean geometry, but I think it's probably more productive for me just to work problems with you at the moment, and kind of remind you of things that maybe you forgot about, or maybe not, I don't know. Let me not be like this. Can you guys tell me if this is angle alpha, if this is angle beta, and this is angle gamma, what can you tell me about alpha plus beta plus gamma? It has to be 180 degrees, right? Now, that's true in Euclidean geometry, all right? As long as we're talking about flat triangles, that's true. If we're talking about triangles on a curved space, this is no longer true. For example, check this out. If I take a sphere, right, and I take a quarter of the sphere, if you can imagine this quarter of the sphere here, right? And if you look at that quarter sphere, if you've got a good imagination, you can see that you can have a right angle here, here, and here. All right, so think about like the equator getting crossed by like the prime meridian, right? Then it makes a right angle where they cross, right? Like locally. And there's a right angle up at the North Pole where they cross. And then if you have another, one like that. So you get this, it's basically 1/8 of the surface area of the Earth, right? But if you look at this triangle, you've got 90 degrees, you got 90 degrees, you got 90 degrees, right? So this curved triangle has sum of the angles equals to, in fact, 270 degrees. That's weird, right? Maybe you haven't thought about this before, but the fact that the sum of the angles in a triangle is 180 degrees is actually tied to the idea that the geometry is Euclidean. We'll talk more about this. This is just kind of a precursor. Now, in your homework, I think I have something. There's a homework problem where they give you a triangle has, I have one that's got like a 14 degree and a 62 degree. What's the measure of the third angle, right? So like if this is 14 degrees and beta is, what my problem is 62 degrees, what's gamma then? So we've got 14 plus 62 plus gamma equals 180, which tells me that gamma is 180 degrees minus 14 minus 62, right? which means that the angle that I'm missing, what do we got, 76, 104 degrees, right? Does that make sense? So we have to find the third angle so that the sum of the angles is 180 degrees, because we're not talking about some crazy curved triangle, right? We're talking about triangle in space here. Example 9, flat space. So we'll talk more about curved space in a future lecture, okay? Example 9 here, you guys remember perimeter? So here's one. You've got a figure like this, and it's got right angles like that. X is here, Y is here, and they want us to find the perimeter of the figure and find the area of the figure. So what's the area? Is X times Y, right? What's the perimeter? That's how far, if you were to build a fence around it, right? That's how far it would be. So you got X plus Y plus Y. In other words, 2X plus 2Y is the perimeter. Now the problem in your homework actually has numbers, but I think you can do that, right? Example 10, I'll fit it in here, is what's called a parallelogram. So a parallelogram is formed by two sets of parallel lines. That was supposed to be straight, sorry. I tried, and I failed. But anyway, you're given, in mind, I'm given that this height right here is 5 feet, right? And I'm given that this down here is 16 feet. And I'm also given that this distance over here is 7 feet. And again, I'm asked what's the area and what's the perimeter. So can you guys tell me for this one? What's the area? What's the formula you use? It's called base times height, right? What's the base? What's the height? So here the base would be 16, and the height would be 5. So that would give us 80 square feet. That's the area. What's the perimeter for this one? So we got what? 16, 2 times 16, right? To get the, let me kind of do some color coding here for a second. So like this edge and that edge gives me 2 times 16, right? And then the sides, right? Here and here gives me plus what? Plus what? Plus 2 times 7 feet. So what's the perimeter? You add those together, you got 32 plus 14, which is 46. Thank you. 46 feet is the perimeter. So those are kind of fun. Any questions about these? All right. Well, I think that's a pretty good place to stop for today, and I'll pick up there next time. Thanks, guys. Yeah. Oof.